Hello everyone. Thank you for joining PrestoCon Day 2022 and this session. In the next 20-25 minutes, I'm going to talk about how to build a modern data platform and why Presto plays a key role in it. I will do a high-level overview of the data platform architecture and Presto benefits and use cases. But let's start with a short introduction. My name is Denis. I'm very passionate about data engineering, data analytics, and data infrastructure. I have a Java engineering background, and I like DevOps culture very much. For almost 2 years, I've been working at Platform24 Healthcare. The company was founded in 2016 in Sweden, and today we are the market leaders in Northern Europe. So what do we actually do? We create a SaaS platform for healthcare providers to enable them to provide digital healthcare to their patients. So it's B2B business model. Now with some context, let's move forward and talk about the actual problem. Okay, the company started with the main focus on the actual services. So in the beginning, on the data analytics side, the scope of needs was very small. Just a few daily and weekly reports and pretty simple BI dashboards. The main limitation was and still is that healthcare is a highly regulated domain. So in our case, we cannot use the solutions offered by public cloud providers like AWS, GCP, or Azure, because the companies are owned by non-European owners. So custom ETL and data warehouse architecture have been chosen as the initial solution. So to be more specific, the data warehouse is based on MariaDB, and ETL scripts run every night in a private cloud. But as business grows, ETL has work with more and more data from more and more customers. As a result, we have known data warehouse problems. It's getting slower and slower. It's very expensive to scale, and if ETL runs during working hours, it affects our end users and our dashboards. So the decision was made, we need to build a new data analytics solution from scratch. And there are the following requirements to it. It should be based on open source software only. The solution has to be self-hosted, cloud native, and Kubernetes friendly, because we want to run it by ourselves and be flexible with the end environment. It has to be reliable as well as scalable and cost-effective. We need to be able to scale horizontally for more customers, data source, and use cases like data science and machine learning. So we started with a new architecture. In this architecture, we used some principles of building cloud-native data platform. I'm not going to cover them all, but the main principle is decoupled storage and compute layers. They have to be dedicated software solutions running on a dedicated hardware, which suits the best for specific use cases. Also, we decoupled computation layer into 3 responsibility areas: data ingestion, data processing, and data serving. The idea is to minimize the effects on each other. So if something goes wrong with processing, it should not break data ingestion or data serving. And the last but not least data platform building block is the orchestration layer, which is needed to manage multiple data pipelines and other workloads. So let's start filling in this concept, and let's start from the orchestration. And among other alternatives, we found that Apache Airflow suits best our needs and requirements. It's open source, mature, and very popular solution. It's actively developing and evolves. It has a lot of integrations with other popular and modern products. Also, it's extensible, so we can easily add missing or customize existing functionality and integrations. It's horizontally scalable, and we can adjust our so it could be adjusted to our current workloads. And there is no single point of failure because each component, scheduler, web server, and workers can have multiple replicas. And finally, there is an official Helm chart to deploy and manage Apache Airflow in Kubernetes. Okay, let's put it to the architecture diagram. Great. Now we have placed the first building block to the data platform, and let's continue with storage. For the data storage, we choose high-performance object storage called Minio. It's open source and Kubernetes native solution. It's also fully compatible with S3. So it could be just used instead of AWS S3. It's horizontally scalable and highly available solution. Minio stores data redundantly to prevent data loss and secure, of course. There is a Minio operator for Kubernetes and official Helm chart to deploy it. Okay, we filled in storage layer, and it's time to talk about computation. Probably there is no big surprise that Apache Spark has been chosen. It's open source and actively developing framework for distributed data processing. It's also horizontally scalable solution which aimed for high throughput. It has multiple APIs like Java, Scala, Python, and SQL. It supports streaming and can run on Kubernetes clusters. In our case, we use long-running Spark Thrift servers to execute SQL queries with minimal delay. Yeah, unfortunately, there is no official Helm chart to deploy it, so we have developed our custom Spark Thrift server chart. Let's check what we have on our architecture diagram now with Apache Spark. And we use Apache Spark for ingestion and processing, but there is some problem with serving layer or serving area. In the serving blocks, Spark covers the use cases which require high throughput, like reporting on demand or machine learning. But many use cases require low latency access to the data. So, for example, business intelligence, data exploration, and ad hoc analysis. So how to solve this problem? And the classic solution is to use data warehouse here. So in the last step of the data processing, the results are copied to data warehouse, from where they can be accessed by users with a low latency. Sounds okay, but it's data warehouse again, right? And data warehouse breaks the main cloud native data platform principle. It uses coupled storage and computation. It also some data sets we produce need to be stored in two places: in Minio for high throughput and in data warehouse for low latency. So in this case, there is no single point of truth. So how can we solve this problem? And could we find a better solution? And trying to answer this question, Databricks formulated Lakehouse architecture in 2020. On this diagram, you can see the evolution of data platform architectures. That data warehouse on the left side, and it's our original solution. Data lake from the previous slide in the center. And finally, Lakehouse, where all data stored and consumed from one place. So what could help us to complete the solution and build Lakehouse architecture? Yes, it's Presto. And that's why it plays a key role in cloud-native data platform architecture today. So finally, we are going to talk about it. It's fully open source, so there is no paid features, right? It's massively parallel processing SQL engine, which allows to read data with low latency. With Presto, it's possible also to access and combine data from many different sources using unified SQL interface. It's horizontally scalable solution, so it could be adjusted to current needs. Also, Presto is Kubernetes friendly by design because it's stateless. Unfortunately, there is no official Helm chart at the moment for Presto. So I have implemented custom and a pretty simple chart to be able to run Presto in our environment, in our data platform. Great. So now we can make the final step in our new data platform and replace data lake architecture with Lakehouse architecture. And also we can call it open Lakehouse architecture because it's implemented with open source software only. Yeah, great. And now when we have everything in place, I want to focus on a few features which makes Presto the best choice here, especially when you compare it with some competitors. Yeah, and yeah, Lakehouse architecture comes with new data formats. With Parquet or Aura tables, you are limited by append or insert overwrite operations. But using Delta Lake, Apache Iceberg, or Apache Hudi, we can change our data sets on a row level by updating or deleting specific records or records by some where condition. So actual change happens in ACID transaction. So there is no risk to leave your data set in inconsistent state. They allow to execute time travel queries to read previous data snapshots, and they have schema evolution support as well. And all three formats have native support in Presto. And native support means that Presto can read those data formats without delegating actual work to any third-party system. So whatever is used in your data processing, it could be available to read by Presto. That's modern, that's good. Yeah, that's great. Okay, now I want to talk about high availability. You won't be able to see up-to-date data if something goes wrong in the data ingestion or data processing layers, and you won't be able to see the data at all if on your dashboards if something happens with Presto, which makes it critical component in the data platform. Originally, Presto Coordinator is a single point of failure in the cluster, and also may become bottleneck in the environment with many heavy queries. If it goes down, then the cluster becomes unresponsive. So how to achieve high availability for highly critical Presto in this case? And traditional solution is to have multiple Presto clusters behind gateway or some kind of load balancer. I think you can find a few implementations of this pattern, but the end solution might be a bit complicated to deploy and manage. It could be less resource effective and not very flexible, especially for small setups. But fortunately, there is another solution. Today, it's possible to run multiple coordinators. It eliminates single point of failure problem, but also it allows to scale coordinator horizontally. So there is no potential bottleneck as well. This new architecture assumes running a new Presto component called Resource Manager, which is responsible for building a global view of the cluster. Our custom Helm chart does not support this feature at the moment, but we have it on our roadmap, so it will be added soon. And the last feature I want to talk about is data virtualization and the ability to build virtual data lake with Presto. In a data virtualization pattern or architecture, data stored physically in a different places and in a completely different systems and formats, but could be accessed by one tool. It's very powerful feature and a very powerful architecture, which could be used for BI, data experimentation, data exploration, and prototyping. And with Presto connector architecture and federated query support, we can implement it, we can use it. So it's possible to build virtual data lake over your organization data landscape, including relational databases, cloud data warehouses, classic data lakes and lakehouses, column and white column storages like Cassandra, K-value Redis, Elasticsearch, Kafka, and even metrics from Prometheus. And yeah, that's it I had to talk about. Thank you for listening to me, and your questions.
Thank you, Denis. We do have some time for questions, so I see a few here. I'm just going to ask you live. Does that work?
Yeah, of course.
Sure. Okay, so one question is, are you using Iceberg or Delta for ACID, etc.?
We use Delta Lake, just because at the moment we started our journey, Delta Lake had better support for merge operation. But as I say, today we are, okay and very flexible. So I think it's not a big problem for us to migrate from one format to another. But yeah, we use Delta Lake.
Great. Another question, do you self-manage your Presto deployments? If yes, how much effort does it take? And what is the size of the team that's working on it?
Yeah, it's self-hosted and self-managed Presto. As I said, just because of our limitations. So we cannot, or it's not very easy to delegate this to someone else. But of course, probably in the future we will use some kind of commercial support. Yeah, I think it's very small team at the moment who manage it. It's me and our core or platform team.
Great.
Am I answering your question?
I think that answers it. Pavel, if it doesn't, feel free to pop another question in there. But a follow-up is, did you solve the auto-scaling on your own?
After scaling of Presto, right? I think.
I'm assuming, yes, it's Presto.
No, at the moment. It's also on our roadmap to implement auto-scaling for Presto. It's not so hard as I know. So I mean, it's also on our roadmap to add in the nearest future, maybe next development iteration.
Cool. And then, are you running in AWS or Azure?
We're running in private OpenShift cluster. It's very specific. It's private, very specifically certified cluster. So
great. Okay, I think that's it for questions. Keep them coming. I think, Denis, you'll be around to answer if folks have more. But we are through the morning session, everyone. So thank you. We have a quick break, about a 20-minute break.